Okay, we are given this problem that says that they give us a diagram and they say given angle 1 is congruent to angle 2, and they have it marked, and AE is perpendicular to BD, so AE is perpendicular to BD. And right off the bat, I would say, okay, well, if they're perpendicular, then we've got right angles going on there. And make that a better looking right angle. And so, and they also said that AB is congruent to DE. So AB is congruent to DE, and they're saying prove that C is the midpoint. So this point right here, they want us to prove that that's the midpoint. Well, to prove that something's a midpoint, we have to show that the two segments that it separates are equal to each other. So we have to show that BC is equal to CD. Once we show that, then by definition of midpoint, we can say that C is the midpoint. But to show that BC and CD are equal to each other, we probably have to show that the triangles are first congruent to each other. So to show that the triangles are congruent to each other, we have to show that their corresponding parts are congruent, whether it be sides, angles, or what have you. So we have to start there with the parts of these triangles showing congruency. So I would say that since this is what we're given in red and green, well, actually not, we weren't given the point yet. I would say that we should also look at, and we are also given this in blue, we should look at the fact that, okay, we've got our two right angles, we've got our two sides that are congruent to each other, but we've also, we're told that 1 and 2 were congruent. Now, they're not inside the triangles, but we can use the fact that they, angle 2 and its partner here, angle, its pair, its other part of the pair, whatever, this pair of angles make 180 degrees. And at the same token, these two pairs, these two angles that create a pair make 180 degrees with this line here. So what I wrote over here was the fact that, okay, starting with this one here, we have 180 degrees, which is a line, and if we take away angle 1 from that 180 degree line, we're left with this angle here. So we're left with this little angle in blue, which is angle BAC. And at the same token, if we go over to this line, which is a 180 degree line, and we take away angle 2 from it, then we're left with this angle here, DEC. But since we were told that angle 1 equals angle 2, so I put a little equal sign there, and 180 equals 180, then it's just logical that if you have the same things being subtracted from the same number, then that would mean that what's left over must also equal each other. And that's actually an axiom from Euclid. That's one of his 5 axioms that says, and let me find that here. Here it says that, I wonder why, oh okay, it's not showing up. So it says that if equals be subtracted from equals, so we had, over here we had, I think it was angle 1 was subtracted and angle 2 was subtracted, both from 180. So it says if equals, that's these two right here, they're equal. If equals be subtracted from equals, okay, then the remainders are equal. So this was, I believe, how is that written? Angle. BAC and DEC. So that was, whoops, BAC and DEC. So then these remainders are equal. So if equals are subtracted from equals, then the remainders are equal. So with that, then, we can conclude that BAC is equal to DEC. So if these equals, angle 1 and angle 2, are subtracted from the 180 lines, then what's left over, these little angles here that I have with the dots, must be equal. So if those then are equal, then by angle, angle, side, and here we have angle, angle, side, by the angle, angle, side theorem, the two triangles are congruent. And since the two triangles are congruent, their corresponding parts are congruent, and BC here corresponds with CD, so they must be congruent. So if these two are congruent, then this little point here in the center, the midpoint, cuts them in half. That's the definition of a midpoint. So we can then conclude that C is the midpoint because it makes two equal sections on either side of it, two equal line segments. So that's how we're going to prove it logically, but now let's go ahead and prove it, really systematically and in a very detailed manner. So you can see right here, this exercise, they've already placed some statements on here, and I've just filled in what was given. And so now we're going to fill in the rest of the slots. So now it looks like they start out 1 and 2 here with exactly what I have written here. However, they put the angle first, like they put angle BAC on the left. So I'm going to just go ahead and rewrite what I wrote here exactly the way that they wrote it. I think my way is easier to understand because when you look at a supplementary angle, you usually in your mind, you start out by saying, okay, 180 degrees, 180 minus angle 1 equals the other angle. However, they're starting it with, okay, this other angle equals 180 minus angle 1. I just don't think your mind works that way, but since they wrote it that way, I'm going to go ahead and rewrite this with the angle on the left. So they said that angle BAC, and I should write it in green since I wrote the other one in green. They say angle BAC equals 180 minus angle 1. And then they also say angle DEC, so this one here, DEC, this little angle, equals 180, angle DEC equals 180 minus angle 2, which is exactly what I have written, only we flipped it. So, so now using the same logic that I used up here, we say, okay, well, let's just, before I go into my logic, we have to fill in our reasoning here for why we wrote these two statements. So, how are we allowed to say that, you know, if you take a line and subtract one of the pairs of angles off of that line, you get the other pair of angle. You get the other angle pair. How can we say that? Well, let's look over here. They're calling it the linear pairs postulate, and that's for both of these, obviously. And it's saying the same thing, they're just giving it a fancy title. It's just saying that if you have linear pairs, you know, if you have a line, and we have a line, and there's a pair of angles, a pair, angle 1, and then this little angle here, that the two angles add up to the 180 degrees. And if you take one angle away, you're left with the other angle. So, so that's the linear pairs postulate, and I have it also written over here. So let me just make another line. Okay, so it's four statements, and they're all saying the same thing. So then we'll go down to number 3. So now they're saying, okay, well, we told you that angle 1 here is congruent to angle 2. That was given. So now we want you to make a conclusion. You know, we took this 180 degrees and we subtracted two equal angles. So I'm going to mark it over here on my diagram that these equal each other. And of course 180 equals each other, equals itself. So what can we conclude now? We've got 180 minus the same angle. So what can we conclude about the remaining angles? Well, we can conclude that they equal each other. So let's go find that. Those angle BAC equals angle DEC up here. Okay. And how can we conclude that? What is the postulate or theorem or definition or what have you that lets us make this conclusion? Well, I like to use Euclid's axiom, and it says that down here, if equal things, okay, if equal things, these two are equal, be subtracted from equals, the remainders are equal. And that's Euclid's, one of his 5 axioms that he built everything on. His 5 axioms, here's his 5 postulates. But here's his 5 axioms where everything, began. So, a lot of people have taken his axioms and they've given them titles. Now, this one, if equals be subtracted from equals, the remainders are equal. There is one file that I have, and they are calling that, where's the file? They call it the subtraction property of equality. And it says the same thing. I mean, it's Euclid's axiom. And it says if the same number is subtracted from equal numbers, then the differences are equal. And so this particular publisher is calling it the subtraction property of equality. This proof, however, let me erase this. It's always hard to find that. Well, it's not going to let me make a bigger eraser. So, this publisher is kind of calling it even something different. He said that we can conclude that BAC equals DEC because we could substitute in, since these are all equal, we can substitute L2 in for L1, L1 in for L2. We could substitute L2 in up here for L1, and we could say L2 equals BAC. I mean, L2 equals up here, and not that it equals BAC, but that we can just use it in place of L1. So I don't really like their reasoning. I would use the subtraction property of equality, or call it just, Euclid's axiom. Let's see, where's the one that they used? Substitution property of equality. So, so like I said, I wouldn't use that. I would use just the subtraction. I would call it the subtraction property of equality. I think that's easier to see. And that's Euclid's axiom. That comes straight from Euclid's axiom number 3. So anyway, so now we've said that, so let's mark so far what we have. we have angle 1 is congruent to angle 2. Okay, that's already marked. So now we've stated that BAC equals DEC. So now we've said that BAC equals DEC by this subtraction property of equality. So now let's go ahead and see what else our next step would be. So now they're saying, okay, well, we were given that AE is perpendicular to BD. That was given. AE is perpendicular to BD. Well, what can we conclude from that? Well, let's look over here. I mean, what I would conclude is, you know, we've got right angles going on somewhere. So they tell me something is perpendicular right away, right angles will spring up in my head. And so that's right up here. ACB and ECD are right angles. So ACB, let's mark that in a different color. ACB and ECD, this one, are right angles. Okay. So that's good. So we're starting to show that these two triangles are congruent, but we need one more angle or side or something to get to the point of stating that they're congruent to each other. So we have to, I guess we have to put our reason in here. ACB and ECD are right angles. Well, how do we conclude that? Well, that's just like a definition of perpendicular. So here it is here. Perpendicular lines form right angles. So that's how we were able to say that. So then now we have to come up with number 7. And we can see what number 8 is. AB is congruent to DE. That was given. But what can we say in number 7? Well, if ACB and ECD are right angles, we have to conclude, we still have to state that right angles are equal, that these angles are equal to each other. We can't just take that for granted in a formal proof. We actually have to say it. And that's just by definition of right angles. So since they're right angles, we can say that they equal each other now in number 7. So number 6, we just stated that they were right angles. Number 7, we have to state that they're equal. So now they're equal. And then number 8, this was given, AB is congruent to DE. So let me mark that in blue. AB is here, is congruent to DE. Well, it looks to me now like we have we have angle, angle, side, angle, angle, side. So these triangles are congruent by the angle, angle, side theorem. So let's go ahead and state that. So here's the triangles. The triangles are congruent, and the reason is the angle, angle, side congruence theorem that says if you have two angles and a side that are congruent to corresponding two angles and corresponding sides of another triangle, then the triangles are congruent. So we've stated that the triangles are congruent, Now we have to say, well, okay, if they're congruent, then their corresponding parts are equal. So that's what we're going to say in number 10. Well, we can't say they're equal. We have to first say they're congruent. And that's how it is with proofs. I can't jump ahead and say BC equals CD. I have to first state they're congruent. Because here I said that the triangles were congruent. And I can't go from congruent to equal. I have to go from congruent triangles to congruent sides, and corresponding parts of congruent triangles are congruent. That's how I was able to state that. And then I could say that those two sides are equal, because that's the definition of congruence. If you say two sides are congruent, you're basically saying they're equal. So it's kind of silly that you have to go through those two steps, but you have to be very specific with proofs. So now we've stated that they're equal, that these two corresponding sides are equal. So let me go ahead and mark that. And let's see. I don't know, I guess I haven't used black. So they're equal. So since they're equal now, we can conclude that C here, this point right here, is the midpoint of BD. And the reason is because, well, that's the definition of a midpoint. A midpoint cuts a line segment in half. In half means the two halves are equal to each other. When we say something is cut in half, we're saying that the two halves equal. So there you have it. We proved it logically in our heads, and then we went ahead and excuse me. We went ahead and proved it systematically with our statements and our reasons. Sorry about that.